Good evening, everybody. We are welcoming tonight Professor Brad Gibson from Hull University, an Aussie Canadian transplant, or is that a Heinz 2 varieties,
Yes,
we would
right.
say around here. Head of Physics and Maths and Director of the E.A. Milne Centre for Astrophysics at the University of Hull. Brad's work has gained a degree of notoriety, can't say it, by defining the Milky Way's galactic habitable zone, named a top 10 news story of the year by the National Geographic. Determining the expansion rate of the universe, for which their team was awarded the Gruber Prize in Cosmology, and building the world's first liquid mirror telescope observatory. A talk which we had a couple of years back, if I remember correctly.
Mm-hmm.
Brad's 400 plus outreach events over the past 6 years have reached more than 1 million people around the world, including nearly 100 schools and colleges around the UK. His commitment to widening participation and diversity and improving the career prospects of physics students led to his Changing Face of Physics campaign being named best practice in the country by the UK's Equality Challenge Unit. So please all put your hands together and welcome Professor Brad Gibson. Thank you.
Well, thank you very much for the kind introduction and for the invitation to come back and speak with you, at least in 2 dimensions, if not 3 dimensions this time, but let's hope for a better 22 so we can actually do it again face to face, which would be nice. I had a grand time when I was out there with you a few years ago and would love to be able to do that again. It's also a tough act having to follow my PhD student, Kate Womack, who's I think was your last speaker. And all I can do is try and do my best. But yeah, when it's always tough. I've followed her on a number of occasions on a various school events, and she is a tough act to follow. So thank you for giving her the chance to hone her skills. It was much appreciated by her. She had a fabulous time when she was with you. Okay, so let me just make sure this is all working. I'm curious, can you see my cursor moving around?
Yes.
Okay, good. Just so I know what to point at. Okay, so what I'm going to cover over the next, I don't know, let's say 40 minutes or so, is, you know, I sat down a few months ago and started to troll through the papers that have been published in space sciences over the last couple of years, took a look at sort of where the major press releases that had come out over the last couple of years, what areas they were focused in, and tried to compile a list of sort of high impact new things. I mean, a lot of what we do in research nowadays, I don't know, for maybe it's being somewhat flippant, it's a little bit incremental. It's all important. But every once in a while, something big comes along, which is transformational, maybe something we hadn't seen before, something that maybe had been predicted and we just been waiting for a long time to actually see it. And so I pulled out 4 or 5 things that had come up over the last couple of years that answered some fundamental questions and then started a new set of dialogue now about new and exciting directions. And it sort of broadly comes under this topic of what do we know now that we didn't know a couple of years ago. And so it's a very biased set. They're not really all in my area of expertise, but they really did catch my attention for lots of different individual reasons. And I'm sort of very excited to sort of walk you through some of these recent discoveries and things that we've learned just in the very recent past. So what I'm going to do is, these are the 5 things. You don't have to read them all right now. I'll come back to them. And what I'm going to do is, some of them take a couple of minutes, some of them take maybe 7 or 8 minutes. So overall, like I said, something 35, 40 minutes or so of your time. And so where I'm going to start right now is radiation. You know, we've been talking about radiation indirectly by just talking about what's up in the sky and the photons that are coming in and interacting with our eyeballs, whether they're from Venus, Jupiter, or stars. And so this radiation is around us in all shapes and forms. Now, this is one way of putting up what we call the electromagnetic spectrum. When we talk about light, we can characterize it sort of in three different ways. We can talk about the wavelength of the light. We can talk about the frequency of the light, or we can talk about the energy of the photons that make up this light. And if you squint, you may be able to just see these vertical bands of color here in the middle. Those are the optical part of the spectrum that most of our telescopes and our eyeballs work in, which is just a tiny, tiny, narrow part of this enormous spectrum of radiation that is out there. Now, like I said, there's different ways to characterize light. I'm going to talk about the energy of light rather than the wavelengths or the frequency. If you were to take one single packet of energy, one single photon that was a yellow color, if you like, from the sun, that would be sort of where this vertical yellow band is. That is what we call 1 electron volt. And again, you could, if you wanted to, you could talk about it in sort of nanometers or microns or whatever wavelength you like, or you could talk about it in terms of the frequency, 10 to the 15 hertz. But I'm going to talk about energy. So the energy of a typical optical photon that hits our eyeball is about 1 electron volt. So that's just a good number to bear in mind. If you went to the left of this plot, you move into the part of the spectrum where the wavelength is much longer or the energy is much lower. Different way of characterizing exactly the same thing. And if there's a big band there where we sort of call radio waves, and the typical energy of a photon that comes in the radio part of the spectrum might be 1 billionth of 1 electron volt, just say ballpark numbers. You might be interested in knowing where, what frequency or what energy or what wavelength, say the Wi-Fi that most of us are connected to right now, that's sort of in kind of right where the letter C is in the word microwave sitting there. That's roughly the energy / wavelength / frequency that our Wi-Fi works at. As you get a bit closer to the optical, you move into the infrared. Wavelengths are getting a little bit shorter, energy is getting a little bit higher, and then as I say, the vertical bands of the optical. And you move into ultraviolet and then into the X-rays, which are pretty energetic. Typically they might have each photon in the X-ray part of the spectrum, maybe 1,000 times that we have in, say, a single yellow photon from the sun. So you're up to 1,000 electron volts. And as you move over into gamma rays, you're into many millions of electron volts. So there's a huge range there, and our eyes are just sensitive to that tiny, tiny little fraction sitting there in the middle. So just some context in terms of the sort of numbers and the sort of energy involved in these different parts of the spectrum. So now those are wavelengths that we encounter, more or less, in our day-to-day lives, whether it is getting an X-ray at the dentist or the doctors, whether it's radio waves picking up signals from both local sources like Wi-Fi, like the microwaves. Those are, there's quite a range in there, but those high energy sort of X-rays, those low energy sort of gamma rays that we might encounter in our sort of day-to-day lives are nothing compared to the sort of energies that we encounter from exploding stars, supernovae. And so you get a supernova sort of once every decade or so in the Milky Way galaxy. And, it leaves behind spectacular supernova remnants, Crab Nebula, which I'll come back to in just a second. And typically after the explosion, what is left behind? Well, all of the chemical elements that we're made out of, all those the colorful picture you see on the left there, all those different colors of different chemical elements, like magnesium, like silicon, like oxygen. The vast majority of the elements that our planet is made of, that we're made of, come from these sort of exploding stars. And so that's one thing that's left behind, and which is obviously important for the development of life. But what is left behind down in the center of this nebula is a remnant. It's either a black hole or a neutron star, or a rotating neutron star. And a rotating neutron star is what we call a pulsar. It's effectively, a big ball of neutrons with a bit of a crust on top of it. And I will come back to the crust in just a second as well. So that is when these things explode. It's actually quite difficult. If you can catch them during the explosion process, we can learn an enormous amount of information about the nucleosynthesis of chemical elements. And if you're really lucky, you can study the shocks around the exploding star. And that helps you learn not only about the explosion mechanism of stars and stellar evolution, how they form, how they evolve, some of the things that Kate would have talked about at the last meeting. But it also allows you to, because these shocks are so intense and so powerful as they blast out from the star, they have a real tangible impact on whatever is around the star. That can be sort of the atmosphere that's been slowly pushed out, and as shocks go ripping through that atmosphere, it can change those chemical elements. But it also, those shocks interact with the surrounding interstellar medium in the vicinity of the star. And the way those shocks interact with that surrounding interstellar medium allows us to probe the physics of what's happening, not only in the explosion itself, but also everything around that star. And it gives us a probe of the interstellar medium, effectively everything between us and that exploding star. Without that exploding star, it's really difficult to study the region in the immediate vicinity of these stars, because the sorts of energies of the photons that are around are very low, and it's very difficult to pick them up and study the interstellar medium in that vicinity. But when you have an exploding star and the shocks go propagating outwards and they smash into the surrounding interstellar medium, anything that's around there, including things, fundamental particles like electrons, these electrons, as the shock goes blasting through them, the electrons are, before the shock goes through, they're kind of just moving around at mundane speeds and mundane energies. But the shock wave accelerates those electrons and accelerates them enormously. Not only are there electrons floating around these stars, but there's photons. There's the photons from the star that has exploded itself, the things that you're looking at on the picture on the left. Those are optical photons that are associated with the nebula. There are also photons from the cosmic microwave background that are everywhere. If you make a little cubic centimeter with your fingers, you can ask how many photons are inside that cubic centimeter from the cosmic microwave background. It's about 400 or so photons left over from the birth of the universe are passing through that every cubic centimeter around you right now. And those photons are also surrounding and passing by these stars as they explode. And as the electrons get accelerated to incredible speeds and incredible energies, it drags the photons as well. And it's called upscatter, but basically all it means is the energy of those photons that are largely either in the optical, electron volt levels, as we talked about a second ago, or even much lower energy if they're cosmic microwave background photons, those accelerating electrons crank up the energy of any photons that are in the vicinity, from electron volts up to not thousands, not to millions of electron volts, not billions of electron volts, but to trillions of electron volts. These are crazy, crazy large numbers. And it is this amazing probe of everything in the vicinity of the exploding star, as well as everything that's between us and the star itself. So it is this unique probe of all of the matter along the line of sight to the exploding star, as well as in the immediate vicinity of the exploding star. Incredibly powerful probes of material that is otherwise really difficult to observe and analyze. So in 2004, that was, there's an experiment studying that Crab Nebula that we just talked about, searching for the highest energies, the highest energies associated with these photons that have been scattered up from electron volts into the trillions of electron volt region. And this is just each one of the dots on this plot on the left are photons that have been measured by this experiment. And the scale on the bottom, the big number 1 means 1 trillion electron volts. It's 10 trillion electron volts. So if you wanted to see where that single photon from the sun, that yellow photon with 1 electron volt, you'd have to go way over to the left off of the screen, about a meter or so. Well, not quite a meter or so, but half a meter or so on this scale to see where the more typical photons that we interact with would reside. So the detection on the bottom right there in 2004, that's around 80 trillion electron volts, or what we say 80 TeV. That was the most energetic photon ever received at Earth from any astrophysical source since 2004. And that was the record holder for about 15 years or so. And then in a couple of years ago, 2019, another experiment to search for the most energetic photons in the universe discovered photons with energies of 350 trillion electron volts, or 350 TeV, also looking at the Crab Nebula pulsar and the photons around the exploding star. It uses a really interesting experiment, a facility in Tibet, high up in the mountains of Tibet. It's made up of this sort of picture of a cartoon on the left there. It's a telescope, kind of, but it's a telescope that works at detecting incredibly high energy photons rather than the typical photons that our optical telescopes work at. It's a very large array of individual detectors. I think there's something like 10,000 of them maybe. It's spread over 10 acres in this high plateau in the mountains of Tibet. And it detects what happens is, as very high energy particles from the source, they stream their way across the interstellar space between, say, in this case, the Crab Nebula and our atmosphere. And there's not a whole lot to encounter between there. So the things don't change a whole lot from the time they leave the pulsar to the time that we see them. But once they get to our atmosphere, the atmosphere is really, really dense relative to interplanetary or interstellar space. And so high energy particles come in and they hit something in the atmosphere, an atom of nitrogen or an atom of oxygen. And that high energy particle breaks apart, say in this case, nitrogen into its individual protons and neutrons. And so you start with one particle coming in that blasts apart one atom, and then a bunch of particles then come streaming down and they run into other atoms and molecules in the atmosphere, which then spawn more, which spawn more. And so you get this, it's called an air shower that started off as one particle coming in, and you get a whole bunch of detections down on the ground. This is how we indirectly observe the super high energy particles that come in because of the way that they interact with the atmosphere. They get reduced to lower energy when they hit the ground, but it's this creation of a shower of particles that we can then wind these back to figure out what the energy of the particle was, that the photon that was coming in. And this facility has been, just over the last couple of years, has been absolutely amazing at detecting this. And it pushed from that 80 trillion electron volts to 350 trillion electron volts 2 years ago. And again, that point down in the bottom there, this is really a unique probe of the sorts of shocks that come from exploding stars. So if you want to understand exploding stars and the origin of the chemical elements, you need to understand how those shocks interact with the stuff around these exploding stars. And this is the way in which we do it. So that was 2 years ago when we detected that one. The same team has just recently, but probably about a month ago or so, have pushed it from 350 trillion electron volts up to 970 trillion electron volts. I mean, the numbers get crazy at this point in time. They're so big, it's hard to remember what the prefix is. Not kilo electron volts or giga electron volts, mega electron volts. We're up to peta electron volts, more or less. Now, what's really interesting about this detection, it's not simply that it's another big number, because okay, that by itself may not be that interesting. But what is really interesting, and I won't go through the gory details of this plot. The blue points down here are pretty high energy detections up to a few years ago. And each of those detections we can associate with, we can go back and we can look at and say, oh, well, we know that came from the Crab Nebula, or we know it came from this particular pulsar or that particular pulsar. So that's great. These ones that are crazy high energy, these ones that are 970 trillion electron volts, these ones are weird because we can't actually tell where they came from. There's incredibly high energy, but they're not coming from the Crab Nebula. They're not coming from any other pulsar or remnant of an exploding star that is out there. And this dotted point that you see going up, 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 and then sort of dropping off like a cliff, that is what all of the models predicted the high energy, the distribution of high energy photons would look like throughout our galaxy, or looking in this particular direction. It should drop off because pulsars can't create photons of infinite energy. And so the prediction was you'd never find anything higher than about 100 trillion electron volts. That's what every model said, no matter how generous you were with it. And at least up until this year, or maybe a couple of years ago, that was what the data was consistent with. These new detections way out here in red are anywhere from 10 to 50 times higher than anything that we can think of should be able to create those sorts of energies. And so these other lines are sort of made up models that are just guessing that there is some sort of mystical source out there, just a diffuse background of crazy high energy photons that are out there in our galaxy, but they're not associated with anything that we can think of. So we can see that they're there. There is some sort of background of super high energy photons throughout our galaxy, but we can't associate them with anything that we know of. So this was a really exciting discovery that has got a lot of theorists sort of scratching their heads, wondering what is the source? Well, what could generate these peta electron volt energies? We just don't know. So I think if I come back in a year or 2 years, some clever theorists will probably have figured out what is responsible for them. So it was super exciting discovery, something we had not predicted we would see, but it's opened up a whole new cottage industry now, trying to figure out what is this background of super high energy photons. So again, outside my area of expertise, but a really interesting puzzle that we did not see coming until just in very recent times. Okay, so let's look at the next one, which is what we call, I've written it as mysterious radio missions are not aliens. Okay, what do I mean by that? It's probably the biggest mystery in astronomy today. Now, you may have heard of these things called fast radio bursts. They were only discovered in 2007, so 14 years ago or so. We didn't know that they were out there until then. And FRBs are more or less exactly what they sound like. They are bursts of radio emission that are very fast. They just for a very short, intense period of time, roughly 1/1000th of a second or so, huge burst, massive, incredible burst of radio emission, and then it's gone. And the majority of them don't seem to repeat from any particular point in the sky. So they're from all over the sky, and certainly up until the last few years, more or less unknown origin. There was lots of things that have been speculated as being responsible for these fast radio bursts, and some of the merging neutron stars, black holes, and I'll show you where we now stand with some of the most recent works. And much like the discussion of using, say, the air showers that have helped us discover incredibly high energy photons, and it helps us probe sort of the material around the pulsar and between us and the pulsar. These fast radio bursts are also very energetic, really intense bursts, and how those photons move from whatever that source is to where we see them allows us to probe everything that is between us and whatever the source is, even though we don't, up until a couple of years ago, didn't really have any idea as to what the source was. It still allowed you to really get unique insight into the material that's in the immediate environment of whatever it is, and what's between us and whatever it is that's responsible for these FRBs. It was only even up till about 2017, there were lots of press releases out there making claims, some of them from fairly senior active scientists, claiming that these things were so short, so intense, that a potential explanation for them was aliens. And one of the models that came out, and you can Google and read the press releases. This was actually I think it was in New Scientist even. Could these fast radio bursts be powering alien probes? The picture that was formed in some of the papers and some of the press releases that came out in 2017 around these FRBs was something like the cartoon you see there, some sort of planet over there, and then some sort of massive structure in interplanetary interstellar space that is, it's hard to tell from the scale, but this is like a giant, almost like a solar sail, but it's a sail that is twice the size of planet Earth, for example. So something we couldn't construct, but maybe some advanced civilization had this massive sail, and on the planet they would have the ability with some intense beam of energy that they would be blasting at this sail, and that radiation pressure would accelerate it to faster and faster speeds. And every once in a while you would get some leakage of this intense energy beam. And you can sort of, depending on the screen you're looking at, you might see some of the red bits escaping on the sides of the gigantic solar sail. And so that was the claim that was made in some of these press releases and some papers as well, looking at what the sort of energy requirements were and the likelihood that you would have some of this radio beam leakage every once in a while, and you would get this random burst of radio emission that we would see when some of that light leaked from the light sail. The first evidence for what was responsible for these FRBs only came 2 years ago. This paper from Bannister and team. Like I said, the sky, we've discovered, I don't know, there's hundreds, maybe a couple thousand of these FRBs have been observed thus far. And up until 2019, basically one would go off and you would detect it. But most of the radio telescopes at the time that were being used for these surveys, they are large collecting areas like Arecibo and Jodrell Bank. But they're great light buckets, but they don't have the ability they don't have high spatial resolution. So you knew that in some vicinity of the sky, something had gone off, but it was impossible to associate the radio bursts with anything in particular because it'd be thousands and thousands of objects in that field of view. And it could have come from any of those objects. And because the vast majority of them don't repeat, because you can stare sort of somewhere and you're eventually going to see one, but because you don't have the spatial resolution, you couldn't associate it with any particular object. And so this really changed in 2019. So anyways, I guess another segue, there was a lot of speculation because they're sort of all over the sky. Most of the thinking was, yes, they probably are extragalactic. They were not all tied to the disk of our galaxy. If they were all really nearby bursts of radio emission from nearby objects, when you plotted them up on the sky, you should see them all sort of working their way around the Milky Way, around the plane of the Milky Way. And they weren't, they're sort of spread all over the place. So that meant they had to be either maybe in the halo of our galaxy, because they could be spread anywhere throughout the halo, or more likely they were some extragalactic source, since galaxies are, again, spread all over the sky, no preferred direction. And this one on the left is, well, this little spike that you see. This is a measurement of the flux density of the radio emission. The numbers don't really matter. It's very narrow. It's a few milliseconds, a few thousandths of a second, and very intense, and then it's gone. But this one, they had the right facility with high spatial resolution, and they were able to associate it with this galaxy, which has this beautiful name, Galaxy A. And that little circle that you see is, they were able to pinpoint exactly where this fast radio burst came from. And it's clearly coming from that galaxy, which is at a fairly high redshift 0.3. So it's not very close to us. It's pretty far away. It's about four kiloparsecs from the center of this galaxy, and we're what, 8 kiloparsecs from the center of our galaxy. So whatever is responsible, it's coming from this galaxy at extragalactic distances, and it's about 4 kiloparsecs away from the center of the galaxy. It doesn't tell you what is responsible for it inside of the galaxy, but it was the first evidence that they do live in big galaxies at great distances. It could have been, like I said, something to do with black holes, something to do with taking two pulsars or two non-rotating ones, neutron stars, and merging them together. Those are some of the favored options, not the only ones, but the favored options for what these FRBs might be. But this was the first evidence they really are extragalactic. So that was super exciting discovery. And then last year, I guess, earlier last year, just as we were in sort of first month or two of the pandemic, this team that's led out of the University of Toronto in Canada were able to detect a fast radio burst. And on the right, you'll see this, again, one of these signatures of an intense burst of radio emission that's confined to a very short period of time. Again, sort of in milliseconds, as we say. But the exciting one of this one is that it is one that's actually inside of our galaxy. And they were able to pinpoint exactly what object was responsible for this FRB. And it's something called a magnetar. A magnetar, I've spoken a lot about neutron stars and rotating neutron stars, which we call pulsars. If a neutron star has a really intense magnetic field, it's called a magnetar. This one doesn't have an incredible amount of energy, but so it's what we call a low energy FRB, and it's sitting right inside of our galaxy. And if it had occurred, if this thing had occurred in a galaxy in the Virgo cluster or Fornax cluster, it would have looked, to all intents and purposes, like one of the high energy FRBs that we see 100 times further away, similar to the one I showed you in the previous slide. So it is a low energy one, but it's a unique one because we are able to actually tell that it actually came from a neutron star with a really strong magnetic field, about 1,000 times stronger magnetic field than normal. I talked about what a pulsar is. It's mostly a whole bunch of neutrons, and they have a thick crust. It's about a mile thick crust of really neutron-rich material that wraps around the pulsar, the neutron star. And there's a magnetic field, and this magnetic field threads through the crust and into the core. The core is sort of churning. The crust is more or less a solid crust. The core is churning around. So the magnetic field, as it goes through the crust and into the core churns it up, and it moves the magnetic field around, and churns and churns and churns and twists and torques and pushes and pulls. And every once in a while, because the magnetic field is so strong, it's able to crack that crust, that mile thick crust. And whenever you get that snapping of the thick crust, you get this intense burst of radio emission, an FRB. And so this is the first, and just in the last year, 18 months, we've actually have definitive proof that at least some FRBs come from these pulsars with intense magnetic fields that are intense enough that they can crack the crust on the surface and drive that burst of emission. It doesn't mean that every single FRB is the cracking crust of a magnetar, but at least some of them are. And that is proof of a lot of the theories that existed at the time as to one of the sources of these potential sources of FRB. So it solved, at least partially solved, one of the most exciting mysteries that has been over the last 15 years or so in astronomy. Again, there could be other ones out there. Some of them could be merging neutron stars. Some of them could be a neutron star merging with a black hole. There's lots of other ones that could potentially drive an FRB, but at least some of them, we know exactly what they are now. And that's not something we could have said 18 months ago. Okay, number 3, everyone loves exoplanets, and it's one of the hot topics in all of the space sciences. And it's kind of been the holy grail has been to try to witness the birth of a planet. And we can go back to 2015. It's not that long ago. In fact, that's when I moved to Hull. That was really the first really clear pictures that emerged of a planetary system that was in the midst of forming. Now, this is a disk of material around a protostar called HL tau. And that disk of gas and dust is ultimately where the planets form. And you can see the various dark rings, which is where planets are starting to form. And as they move around in orbit around the protostar, they're hoovering up all the gas and dust and chunks of rock and getting bigger and bigger and bigger and bigger. And you can see the hollowing out effect as this planetary system is forming. What you can't see, there isn't any image of the planets themselves. The evidence that they're in there is there in the picture, but the contrast against the protostar is such that you can't actually see the planets themselves. The first sort of picture of a newly born planet was just a few years ago. That was in 2018. This has been a highly processed image here, which is sort of with blanking out where the protostar is down in the center. It's called PDS 70. And that bright dot that you see to the right of the blacked out area where the protostar would be is the formed planet. It's not a picture of the planet sort of being born. It's newly born at this point in time. And that was sort of the holy grail, was to find something in between, something where you could actually see the planet itself forming, not just the evidence in the rings on the left, and not sort of the final product at the end, but capture that growth on the planet itself as it starts to hoover up and pull in material and grow. And we've actually been able to do that just over the last year using the European Southern Observatory, the very large telescope, it's high up in the Atacama Desert in South America. And one of the facilities one of the instruments on the VLT is this one called Sphere. It's an amazing, we'll call it adaptive optics imager that is able to, in small fields of view, is able to effectively eliminate the disturbing effect of the atmosphere that blurs all of the point spread functions of the stars, and it uses this clever technique, like I said, called adaptive optics. And so you get these beautiful crystal clear images, but more than that, it's also able to do polarimetry. And polarimetry is, we encounter it if you have polarized lenses and sunglasses when you're driving. You want to be able to minimize some of the scattered light, and so you put on your sunglasses, and it blocks some of the light. You have light can be what we call left polarized, left circularly polarized, right circularly polarized. And And so you can block some of the light. It's a great way when you have a star and a planet. Usually, the star is so much brighter that the reflected light off the planet it just gets completely swamped by the star or the protostar itself. When you use polarimetry to sort of filter that light down into its constituent polarizations, then you're actually able to, very recently, within the last year or two, actually able to reduce that contrast enough that you can see the planets not only after they're born, like in the previous image, but now we can actually see them right in the midst of forming. And that's what this image on the left is. Well, all of these images, they are highly processed but data collected by this polarizing imager, this thing called Sphere on the VLT. And what you see here on the left is a protostar system. If you were on Earth, the numbers may not make a whole lot of sense. This 0.2 arc seconds means that this thing is incredibly well resolved. If you were doing this from the ground here, all of the features that you sort of see in this image would all be blurred together. You wouldn't pick out all these subtle details at this sort of level. But we can do this with this adaptive optics imager that also allows you to filter out the polarized light. And what you see, well, down in the center is where the protostar would be, and you can see these sort of spiral features that are coming out around it, moving in a counterclockwise way. And on the image on the right is sort of zoomed in on that inner region, and there's this little feature called F1, which is what this blue twisted thing here on the right is, and overlaid in green is what all of the theoretical predictions suggested you should see from a protoplanet that's in the midst of forming, in the midst of pulling in material. This twisted blue thing is exactly what the models had predicted. The little kink that you might be able to see in green is the theoretical prediction, and the observations line up absolutely perfectly. This is the clear signature that there's a protoplanet down here, which is, you can sort of see the numbers there, 5 to 10 times heavier than Jupiter, at a distance which is about 80 astronomical units. So it's about the same distance as Neptune, let's say, is from the sun. So it's a big planet, about the distance of Neptune from the sun, and we can see the clear evidence of the planet forming now. It's not newly born yet, and we're not seeing the fully hollowed out aspect of the protoplanetary disk, but we have the first clear evidence that planets accrete and grow and pull material in exactly the way that the theory had predicted. So it was a fantastic success for the theory of planet formation, but the first observational evidence of actually capturing that planet formation at its earliest stages. Again, a very exciting thing that 2 years ago, we didn't have that picture. Yeah, we believed that the theorists were going to be correct, but this was the first clear evidence that this is exactly how planets do accrete material, and it was a resounding success for the theoretical predictions at the time. Next one, coming back to black holes, but not the little black holes that I kind of alluded to before, stellar mass black holes. Now we're talking about supermassive black holes. All of you have probably seen this image from a couple of years ago. It was probably the space image of the year, space image of the decade. Got an enormous amount of attention. It was covers of every newspaper and magazine around the time. It was, this picture of a black hole. The ring, this nice smiling face that you see, the ring, which is the captures the way in which light gets bent enormously when you get close to a black hole, and it's sort of the theoretical model of what it actually looks like, and the various bits are, you're able to see. On the bottom here is actually the underside of the disk, but you're actually seeing it warped by the extreme gravitational field of the black hole. And the bit at the back is actually part of the disk. Again, the light has been bent. So even though physically it might be a disk. We're seeing it bent and projected up onto the sky because of the way the photons get bent moving around the vicinity of the black hole. And we know the mass of the black hole is about 6.5 billion times the mass of the sun. We know that this black hole is rotating, what they call a Kerr black hole. And it got an enormous amount of attention because it was a unique, resounding success for another resounding success for Einstein's theory of general relativity. And it allowed us to probe that gravitational field on scales that had never been accessible before. And so we maybe come to expect Einstein's always going to be right. So maybe in some sense, it may seem anticlimactic, but it was something that we just never been able to test before 2019. So this really was an incredible discovery, an incredible impact, and not only within the scientific community, but in terms of public outreach and engagement, and talking about black holes and pictures of black holes for the first time. So it was really exciting. More recently, just in the last month or a couple of months or so, we've actually not only been able to, and there's lots of press releases out there. There's now movies of this showing the flickering of that smile down on the bottom, if you like. But more importantly, what's come out in the last month or so is, I talked about polarimetry just a second ago and how we were able to filter some of the light to get these pictures of planets in the earliest stages of formation. People now have been able to do the same thing by using the same polarimetry techniques, but now applied to this black hole in the center of M87. And it may not show up on your screens, but there are a whole bunch of wispy lines that are sort of cutting across here. And those are the lines of polarization. And what is that actually showing you? Well, it's a one-to-one probe of the magnetic field. By looking at those little lines and how they're curled, and then the contrast between them gives you a really good picture of what the magnetic field is around the black hole. And why do we care about that? Well, one of the mysteries that we've had with black holes like this, and a lot of other supermassive black holes, is that there is a lot of gas and dust around them. And that gas and dust, for the most part, happily orbits around it, but it slowly loses energy, and the gas and the dust falls in, and you feed the black hole, and you get intermittent little bursts of energy that come out in different wavelengths as the black hole gets fed. Now, what we couldn't understand was why many of these supermassive black holes weren't gobbling up material faster. Why weren't they being fed more quickly? Why weren't the orbits decaying more rapidly and the gas and the dust falling into the black hole? We should have seen evidence of them feeding a lot quicker than what we were actually seeing in nature. And discovering that these sort of supermassive black holes have intense magnetic fields around them has allowed us to understand why they're not feeding that fast. The magnetic field basically helps prop up that gas and the dust. It slows it down from falling in really, really rapidly. And so it's this slower, what we call drip feeding of the black hole. Again, it was one of those predictions that theorists had made, but until a couple of months ago, we'd never had confirmation, any observations of what the magnetic field was around black holes. Now we do, and we now, for the first time, have confirmation that magnetic fields do prop up the food source of black holes, and it slows down their feeding. And again, another resounding success for theory. But these are the sorts of things you need to have confirmed. And as of a couple of months ago, we finally do have confirmation. And so the last one, just to finish on, and it's a bit self-serving in some sense, but it's sort of driven all of the research a lot of the research that I've been involved with over the last 2 or 3 years now. It's a very, very ambitious computational experiment in terms of the time allocated on supercomputers. It might be the most, it could be the most ambitious. There's between 300 and 350 million core hours. That, those numbers are so big. Using a new supercomputer in Korea, where they gave us basically 6 months of use to do whatever we wanted. If you tried to do this experiment on a single computer, it would have taken about 30,000 years for it to actually run, but we were able to do it over 6 months or so in this facility in Seoul. And what you're seeing on the left is it's a simulation of a large chunk of the universe. It's about 100 times larger than any other simulation that has been done previously in the field. And that fly through you see on the left there, every one of those little dots that you see is a galaxy with millions and billions, tens of billions of stars. So it's a synthetic universe with all of the gas and the stars and millions upon millions upon millions of galaxies that are requiring analysis. So we have just a ridiculous amount of data. Again, it's not gigabytes, it's not terabytes. We're talking petabytes and exabytes, an insane amount. So a lot of the development over the last couple of years has not been science. It's been developing tools that allow us to actually analyze something that is on petabyte and exabyte scales. So we had the first paper just published. If you do go to the YouTube channel link at the top, you can see the entire fly through, as well as the fly through. There's various little bits splitting up, showing you the dark matter, showing you the gas, showing you the stars. Here I'm just showing you the stars with some of the gas overlaid around the clusters of galaxies. It's also accompanied with beautiful, haunting traditional Korean music, which reflects the large, huge contribution that the Korean collaborators put into this amazing simulation. And hopefully for the next 2 or 3 years, that's going to be driving, we're into the data exploitation side of things now. We're really people power limited. I've got one of my other PhD students, Leah Cox, is involved in this project in helping us design the tools that will allow us to data mine this simulation. So very exciting. Hopefully when I come back in a year or so and talk with you, I'll be able to show you some of the amazing things that we've been able to extract from this unprecedented simulation. So I think that's more or less everything I wanted to say. I don't have any sort of conclusion to wrap up on. Like I said, it's a very biased look at some really exciting recent developments over the last couple of years, some of which were confirming things we had hints about, some of which were complete surprises, complete unknowns, but hopefully picked up a few things that you hadn't seen before. And thank you yet again for letting me take up 45 minutes of your time.
Thank you, Brad. As always, fascinating listening to you. You always make us work hard and think hard. So thank you for that. Could I ask you to stop sharing your screen? Thank you. And it's question time. So ladies and gentlemen, as always, I prefer a digital hand, if you can find one. Otherwise, wave at me. I do have 2 screens to scroll through. So persist if you're waving. Digital hands, please. And I'm looking for questions. Tony Morris, fresh from Mid-Atlantic. Tony, nice to see you back. And can we have your question, please?
Really interesting talk that from Brad. Just a couple of questions, if I may. The James Webb Space Telescope goes up next week.
Crossed. Been waiting for that one for my entire career.
Yeah, so one of the things that they'll be looking at there is, I think it's exoplanets. So have you got any view on maybe other discoveries that they could find with the James Webb Telescope? And going back to your last presentation, you mentioned the modelling of the dark matter in your computations.
Yes.
So can you just give us a view on how you do the modelling of that?
Yep. The nice thing about, I'll do the latter part first because it's fresh in my mind. The nice thing about dark matter, well, the bad thing is we actually don't know what it is. That's and 85% of the matter in the universe is dark matter. And so yeah, that is a bit of an embarrassment that we don't know what it is. That aside, whatever it is, it's actually quite fairly straightforward to model inside of a computer because there's the 4 fundamental forces. Kate would have talked about nucleosynthesis last week, and there's the strong force that drives what holds atoms together. There's the weak force that drives radioactivity. There's electromagnetism, we talked about the electromagnetic spectrum. These are all fundamental forces. And then gravity is that fourth fundamental force. But gravity is actually really simple. It's what we call an inverse square law. If two particles, two people, two planets, two galaxies, whatever the case may be, there's a certain force of gravity that pulls them together. If you moved a factor of 2 further away, the gravity goes down a factor of 4, 2 times 2. If you moved it 10 times further away, the force of gravity goes down a factor of 100, 10 times 10. And that's all. That's the only way that dark matter interacts. What really gets complicated in these simulations is the other forces. They're way more complicated to model inside of a computer. So dark matter simulations and the treatment of dark matter, you don't have to worry about light. You don't have to worry about all the other complicated things that drive, star formation and the colors that you see. That physics is way more complicated. It all sits on this backbone of dark matter, but the only physics really is just this, what we call the inverse square law. So the computational techniques get tricky, but the actual physics it's more or less kind of A-level. It's A-level, not even, it's probably GCSE physics, this inverse square law. So it's actually, in a physical sense, very easy to model. In terms of what JWST will do, people keep saying, it's the replacement for Hubble. And it's probably not a fair comparison, because Hubble is mostly sensitive to, those optical photons that our eyes are sensitive to. And JWST works in the infrared. And so that opens up a discovery space that is different than HST. It does mean that, it's a much larger collecting area. Because it's a larger collecting area, you can go fainter, but you've got really good angular resolution. And working in the infrared means this discovery of exoplanets is, like I said, gets complicated when you're working in the optical, because of the stars are just so much brighter than the reflected light that comes from the planets. And you can do your best with doing these clever techniques with polarimetry and the things that I talked about there, but working in the infrared and the wavelengths that JWST is working at, that minimizes the contrast, if you like, between the stars and the planets. So it will mean you'll have an incredible probe of planets in a way that we don't have now, other than the handful of ones that I've just been able to show you. But it's also the best way to probe the very first galaxies that are forming, at very, very, very high redshift. It's a big collecting area. Working in the infrared is a big advantage, because there's some of the light from those first galaxies will get, it's redshifted, which means it gets redder and redder. And the effects of dust extinguishing some of that starlight gets more pronounced. So if we've got lots of theoretical ideas about the emergence of the very first galaxies, but we don't have Hubble has picked up the odd little things at exceeding, extremely high redshift, but JWST will completely lift the veil on the formation of the very first objects. And the hints that we've got now are really exciting, but JWST will just completely transform that field of the first galaxies and the first objects. So it's super exciting for close to home stuff, like anything that is enshrouded in gas and dust. For the formation of stars, star forming regions where you've got lots of dust that blocks a lot of the light, JWST will allow you to probe right down into the hearts of these star forming regions. So the stellar community is super excited. It will completely transform the planetary community and completely transform the galaxy community, particularly those who are interested in the emergence of those very first objects.
Okay, Tony. Excellent. I'm still looking for questions from anybody else. Tony Hudd. Tony, can you unmute yourself?
Maybe not.
Can you hear me, Tony?
Yes.
Right. Good evening.
Good evening.
Can we have your question, please?
Well, it's to do with high energy photons. It seems to me that, and has done for a long time, because each photon will be traveling at the speed of light, whatever medium it's going through. None will be any heavier than the other, and they won't be traveling at any different speed. So what makes, it seems to me that there will be no difference between a high energy photon and an infrared photon, a low energy photon. And I was wondering, the reason I think that they seem to be high energy is because of a hell of a lot of them coming at once, rather than any individual or each individual one being stronger in whatever sense than lower energy ones. Could you explain?
Yeah, so you're right. They do all. Doesn't matter whether you're a radio wave or a gamma ray. You're traveling at the speed of light. Absolutely, 100% right. Their speeds can get altered by the medium that they're going through. As they go through a plasma or a high density region, low density region, that can adjust the. It's kind of like sound. Sound travels at a different speed in the air than it does in water, for example. So the medium that it passes through will have an effect on the wavelength. And so that is partly how we can probe sort of what material it's passing through on its way from the Crab Nebula to us. If there was absolutely a 100% vacuum between there and us, all the photons would arrive at exactly the same time, whether it's energy or whether it's radio waves or whether it's gamma rays. There is there's a lag because of the material that they pass through, but that's part of the way that we probe what's in between us and them. But the photons do have different energies, just like in the sun. You can look up and our eyeballs are sensitive to those photons that are, yes, traveling at the speed of light, but have wavelengths or energies in the optical region. But at the same time, we're also getting, for those of you who are in the Canary Islands, you might have been out, getting some sun, and so you're probably picking up a few more ultraviolet photons as well. They also traveled at the speed of light, but they have very different energies than those optical photons. So there is a spectrum. So even if they are traveling at the same speed, they can have different wavelengths and they can have different energies, those photons. And there is a spectrum in there. And our sun doesn't generate much in the way of any gamma rays. It's mostly in the optical, and the infrared, and ultraviolet. But these objects, these shock waves around pulsars, are able to accelerate and increase the energy of those photons in the vicinity. So you are right. Broadly speaking, they all travel at the same speed, except in very special conditions when they go through different media. But they do have the different energies, each of those photons.
But what is the energy, and why do they travel in waves, and why do they travel all together at the same?
It's this comes back to, it's a convenient way in which we describe light. We can think of it as waves, which is why we talk about wavelengths and frequencies. You can think of them as particles, which is why we use photons and the energy of a photon colliding with something. So it's, Einstein had this picture, wave particle duality is what he described it. You can describe light in these two sort of different ways you can, because it has the behavior of these, it has these kind of two different properties. You know, the light can have, can be thought of as photons of different energy. It can be thought of as waves with different wavelengths and different frequencies. It's, I guess, one of the great successes of Einstein was realizing that you could categorize and describe light in very different ways with very different properties, one being waves and one being particles.
But you separated the the waves and particle and energy, but some people say that the energy is because of the shorter wavelength.
There is a relation, a very close relationship between energy and wavelength, and energy and frequency. They go hand in hand in this, and kind of in that very first plot that I showed, you could have read the wavelength across the top or frequency along the bottom or energy along the way. They are very closely correlated, and you can use any one of those to describe light, any one of those metrics of energy and frequency and wavelength. And you can think of it as a photon, if you like, as a particle, or you can think of it as a wave. It's the beauty and the frustration of Einstein's vision of wave particle duality, as it's called.
If you just had one photon coming at you, it wouldn't be any different to any photon from any source, would it? In itself, just the one. And how many do you take?
It'll have different energy, depending on what sort of energy that particular photon is. But you know, an optical photon from the sun is no different than an optical photon from the Crab Nebula, if you like. You know,
or from a gamma one.
Yeah, and I can, you know, Peter's got the good point here. These various experiments that are done with slits, and how you can sometimes, you know, what wave behaves like you might think if it's a particle, how does it go through, you know, how does it go through these slits the way that they do? And that's because you can also describe it as a wave, or you can describe it as a particle. Yep. So that's a whole other discussion.
Thank you, Peter J, for simplifying the conversation. And Tony, yeah, you're asking some really fundamental and very big questions there. And we've got people stacked up with other questions. Can we leave it there for the time being?
Thank you.
Okay, thank you, Tony. Peter Lloyd.
I was going to make a silly comment on the last one, but perhaps I better not after what you said. No, the question I had in mind, and I almost hesitate to ask this one because I'm not sure quite what it is I'm asking. But in your part 4 of your talk about the magnetic fields slowing down the rate at which black holes gobble things up, I was under the impression that we can never actually see a black hole gobble up anything because of time dilation.
Yeah, I mean,
what is it we're actually measuring?
You can measure the as the material gets, I guess, close to the event horizon, it starts to get shredded, and some of those, the act of shredding that material, even, you know, it hasn't, you know, this is necessarily crossed the event horizon in that sense, but the effect on the gas and the dust it's felt before it crosses the event horizon. So that shredding, as it's approaching, we can see, because those photons do have the ability to escape because they've not crossed the event horizon. So you're indirectly seeing the gobbling by seeing the shredding of the material as it gets really, really close. You're not actually seeing it cross for the various reasons that you say. So you're seeing the death throes, if not the death, if of that material.
Well, thank you. I think I follow. Unfortunately, your sound was breaking up on my reception for some reason. I hope it wasn't for everybody else. But yeah, I think I followed what you were saying. So thank you. Yes, I'll think about it.
Thank you, Peter. Gary Ford.
Hi, thanks, Brad. That was a very over my head talk and really interesting. I've been trying to struggle with questions, but I've got two, if I may. You mentioned in one of your slides about the magnetic fields, the polarized light being an indication of the strength of the magnetic field. I just wondered, is that the only way there is of detecting magnetic fields from outer galactic space, by analysing the polarised light? So that was question one. And question two was, I understand that all electromagnetic waves can be polarised. I may be wrong in that assumption, but I understand, I do a lot of photography, so I understand polarised light and visible, obviously for visible wavelengths. Yeah. But do they do analysis in like polarized infrared light, polarized X-ray? I mean, I've never heard anyone mention like polarized other than visible light. So I wondered, how far that is in, in experiments and observations.
Yep. No, you're right. The light, it depends on, some astronomical sources generate light that is, highly polarized. In one particular, left, right, circular, whatever the case may be. It depends on the source itself, and those are maybe special sources. Most astronomical things, all that, it's more or less unpolarized. Everything's jumbled up. So you have to have the material, passing through dust, for example. That will preferentially scatter light in a certain way so that it filters certain polarization. So it preferentially allows you to see particular polarization. So it's a very nice way to probe some of the properties of dust, for example, in protostellar disks as well. So yeah, it all depends on the medium and it depends on the source, but there's nothing magical about optical light versus infrared light, for example, or ultraviolet light, in the sense that if it's a bog standard source where light's coming out in any sort of polarization, however you like it, then it will be unpolarized. And if you've got the appropriate tools, you can decompose it into its constituent polarizations.
So when they're doing observations, they have to consider all polarizations to get to know whether it's polarized or not. You can't just check for one.
No, I suspect, and there are certain sources and certain, we understand the scattering properties of light off of dust, certain types of dust grains, and so in advance preferentially that one particular polarization is going to be preferred over another. So in that case, you can be guided because I know that this light is going to be predominantly left circularly polarized or something like that, because I understand kind of broadly the properties of the material that the light is going through. So sometimes you do know in advance. Sometimes you need to explore and enter new sort of parameter space to discover that exact thing.
And you did say there's a correlation between the polarization and the magnetic field.
Yes, there is sort of this one-to-one correlation, but it's sort of getting outside my area of expertise at that point in time. So, but yeah, the lines showing that the lines of polarization on that drawing do map apparently one-to-one with the magnetic field. I don't know how the strength of it varies as a function of position along these lines and things like that, but it is a direct measure of the magnetic field strength, and probably the shape of it as well, given by how those things are shaped. Yeah.
Thanks very much. Thank you.
Thank you, Gary. Mick Nichols. Michael.
Hi, Brad. I missed the end of your talk because my laptop decided it wanted to do a Windows update. I saw it up to where you shown that video of a fly through.
Yep.
Can you just explain what that was again, please? Because I missed the end of that.
Yeah, it is just a really gigantic simulation of the universe. And lots of groups are doing this, doing simulations of the universe. And you limit, there's a trade-off. You can have a smaller volume and have, you know, higher resolution for your simulation, or you can have a gigantic volume, but then you've got to give something up, and it means you don't resolve your galaxies very well. And we sort of were able to do both, do a really, really large volume, sort of, yeah, depends on how you do the counting, and between 10 and 100 times bigger volume, but we didn't have to give anything up on the resolution. And so it allows us to, if you're interested in, you know, the distribution of things on the largest scales, which, you know, you get a lot of people in cosmology who are really interested in how galaxies are distributed in the cosmic web. And you know, my interest is more on the individual galaxies. So if I was just doing a giant simulation, I didn't have galaxies that I could go inside of and do some interesting science, I probably wouldn't have been so interested in this project, because the largest scale structure, it's cool, but it's not really my interest. I'm really interested in what's going on inside of galaxies. And so now we have this database of, you know, millions of galaxies that we can dig around inside of, look at the chemistry, some of the stuff that Kate would have talked about in her talk last week. And so it's the best of both worlds in the sense I can do galaxy scale physics as well as the largest scale physics. So, and the only reason we were able to do it was because, yeah, they had a new facility in Korea that they were putting in place, and the co-PI over in Seoul is on good terms with the Korean Supercomputer Center, and they said, okay, we want you to take it through its paces. You've got 6 months, you can do whatever you want. And we didn't have to apply for time. We just got this crazy allocation of time that you would, you know, more than 10, 20, 30 times more than I've ever gotten before on any proposal that I've written. Never would have got it through. If I'd had to put in a competitive grant, they would have said, no, that's an insane amount of time to be doing that. So we had that benefit, and it allowed us to do this amazing simulation.
So it's actually real data then, rather than just simulation. It's a simulation of real data. Yep,
it's real data, and we, you know, currently there's, you know, it's not like you can load it on your laptop when you've got, you know, 1,000 terabytes of data or something, or even more than that, you know. So it is something that we're still trying to wrap our head around, how we actually analyze that much data. Again, my interest is more, I can go in and pull out individual galaxies that I'm interested in, and I can handle all of that. Dealing with, you know, the entire database to do really large statistical studies of things, it's a skill set involves, you know, data scientists and data mining algorithms that sort of go above my head very quickly.
Thank you.
Okay, Michael. So I'm looking around one last time for questions. I can't see any hands. I cannot see anybody waving at me. So, ladies and gentlemen, can I ask you to give a big Mexican Swinton Astronomical Society thank you to Brad Gibson. Brad, once again, thank you for an excellent talk. Thank you for your time.
It's great coming back and seeing you all again anytime. And like I said, let's try and do it again in real life at some point in time.
Oh, yes, please.